Hello everyone, and welcome to this, which is the third in the series of LimitState webinars for 2016. I'm Tom Pritchard, your host, and our speaker for today's session is Professor Matthew Gilbert. He'll be talking to you about how you can use yield line analysis and LimitState SLAB to reveal hidden reserves of strength in reinforced concrete slabs. We aim to show you how the yield line method has been systematically automated and removing much of the uncertainty that the critical pattern has actually been missed. Also how LimitState SLAB can be used to rapidly analyse a reinforced concrete slab and often demonstrate additional capacity when compared with other methods. And finally, I'd like to teach you a little more about the new features in version 2 of LimitState SLAB, such as the ability to model lift supports. The presentation part of the webinar is due to last around 35 minutes, and there'll be about 5 minutes at the end for questions, which can be posted at any time using the question panel that should be present in the webinar interface that you have on your screens. We attempt to answer as many of your questions as we can during the time available, but unfortunately this isn't always possible. However, we'll make sure that everyone asking a question does get a reply after the webinar has ended, so please don't worry if we don't get round to yours. And on the subject questions, if you do have any about the software after the event has finished, please do feel free to email us on info@limitstate.com and we'll be happy to speak to you in detail about them. So without further delay, I'd like to welcome to our speaker today, who is Professor Matthew Gilbert. I'll now pass you over to him.
Thanks very much, Tom, and thanks very much to all of you for joining the webinar today. Okay, so when you think about the yield line method, you might typically think of yield line patterns of the sort you can see to the left of the screen on the current slide. So relatively simple collapse mechanisms. However, now that we're able to systematically automate the yield line method, we can now apply the method to slabs of arbitrary geometry and to obtain yield line collapse mechanisms and, critically, the collapse load factor or required moment of resistance for very much more complex real-world slab scenarios. So all of these slab yield line patterns were obtained using LimitState SLAB, and you can see now on the slide currently showing that we're able to also animate those mechanisms in order to give you a much clearer understanding about the mode of response. Okay, so before I get into the meat of the presentation, just say a few words about LimitState, the company. Actually, it's a University of Sheffield spin-out company, spun out almost 10 years ago, and the main aim of the company is to bring the fruits of academic research out to a wider audience. So providing engineers with powerful software, primarily for ultimate limit state analysis and design. And we're using optimization methods which are not conventionally used in commercial software at present. Because we're a spin-out company, we're able to ensure the applications are easy to use and also are fully supported by our team of engineers in the company. What was our goal in setting up LimitState? Well, one of the key ones was to provide an alternative to mainstream offerings for ultimate or collapse analysis. If you think about existing engineering tools, you tend to think of two extremes, either hand calculations, which may be automated in a simple spreadsheet or software application at one extreme, and at the other, advanced, in inverted commas, tools such as those based on nonlinear finite elements, discrete elements, and a variety of other techniques. And the key thing is conventional offerings don't have anything much in the middle, so there's a big gap between these two types of tools. And what we were determined to do was to fill that gap with what we felt were mainstream tools based on rigid plastic analysis. And we could be talking about applying this kind of technique to geotechnical problems, to masonry problems, and particular interest today, obviously, to reinforced concrete slab problems. So in other words, allowing the user to specify problems of arbitrary geometry, spatial distribution of material properties, and get solutions in the same way as you can with the non-unified elements, but with the ease of use associated with hand calculation end of the spectrum. So these are the tools that we currently have available in the marketplace, tools for masonry bridges, geotechnical problems, and concrete slab problems. And these tools are now widely used around the world in more than 30 countries worldwide. And you can see many of the largest companies in the world are using them. So Arup, Atkins, Balfour Beatty, and so forth. Okay, move on to the meat of the presentation, using the yield line analysis to reveal hidden strength. First of all, what do I mean by the yield line method? Well, it's a means of directly analysing a slab at the point of collapse. Traditionally, it's been a hand method, so what that means is that you would guess a yield line pattern, so a geometry of the pattern. We would then do some simple calculations, which involves typically equating internal and external work, and then we would use those equations to work out either the collapse load or load factor, or in a design context, the required moment capacity to realize a given requirement, or to meet a given design requirement. Pros and cons of the yield line method. Well, the pros are we're going straight for an estimate of the collapse load. Calculations are relatively simple. We don't need to iterate towards that stage. We can just dive in and get an analysis result straight away. In the context of this webinar, the big benefit is that we can get more economical designs using the method than we can using, for example, elastic methods, or if we're dealing with an existing slab, we can get a more realistic assessment of the true capacity of an existing slab. So in many cases, you can find a slab which you thought may need strengthening actually doesn't. There are some cons. The biggest probably has been the first one on the slide. You get unsafe or non-conservative estimates of the strength if you choose the incorrect mechanism. And if you're doing this by hand, then that's a real worry because as engineers we want to sleep easy and we don't want to wake up in the middle of the night thinking, oh God, I've missed that a mechanism which could be more critical than the one I assumed. And I think that has significantly reduced the popularity of the method in recent years. The fact that it's been a hand method and provides non-conservative outcomes. Another disadvantage is it is relatively limited. It does only consider flexural failure, so you will need to, for example, check for punching shear, etc., if needed. Okay, so in terms of application of the yield line method to structures, and first of all, let's have a look at bridges. Actually, quite a lot of work was done in this area in the 1990s and 2000s by Cam Middleton and colleagues, who showed that the strength of many highway bridges, which had been deemed not to have sufficient capacity to carry 40-ton vehicles, he was able to show that actually they did. So what we see on this slide is the red lines showing the elastic assessed capacity and the green line showing the yield line or plastic assessed capacity. So in many cases we've actually got a case where the bridge appears to be capable of carrying 40-ton vehicles. The way that these calculations were done was by cycling through a range of possible yield line patterns, which you can see on the right. And you can see in this particular slide that there's 27 possible yield line patterns. There is, however, always a slight worry that there is a yield line pattern number 28, which hasn't yet been programmed into the computer, which is actually more critical, and which could or would bring down the assessed capacity. Thinking about buildings, a similar time in the 1990s and 2000s, there was quite a lot of work done on demonstrating that yield line design actually leads to reinforced concrete slabs which contain less reinforcement and also simpler reinforcement. So we can see here that floor number 4 in the Cardington European concrete building contains only 14.5 tons per floor, compared with, for example, 23.2 tons with elastic design. It's possible with elastic design to reduce the weight, but then the trade-off is that you end up with hugely complex design, so many different bar marks per floor. Other observations in respect to buildings, building slabs often have quite complex shapes with holes for services and flights of stairs and the like. In the case of existing slabs, if we apply yield line method, then potentially we can avoid the need for strengthening, which can be extremely expensive when it comes to upgrading existing reinforced concrete floor. And in the case of existing buildings again, if you're concerned about serviceability, then you can always actually perform an in-situ test. So in other words, apply service loads and see whether deflections really are an issue or not. Okay, so what I'm going to do is just start up the software, just to give you a very quick taste for what can be achieved. So what I'm going to do is actually, well, there's two options. One is I could use one of the simple wizards to set up a simple example problem. So here's a rectangular slab, and this is such that if I'd entered the appropriate geometry, I could simply click the play button at the top and get a yield line pattern and a corresponding load factor, or as we call in software, additive factor, which is the multiplier on whatever the specified load is at collapse. However, what I'm going to do actually is just start an example from scratch. So I'm going to choose an empty project, and I'm going to draw the slab out using the very simple user interface provided in the software. So I'm just going to click Finish, and I'm just going to use some of the drawing tools are available. Now all the icons around the outside of the user interface are actually color-coded, so the ones I'm going to be interested in now are the blue ones, which is for drawing entities of various sorts. So I'm going to choose the polygon tool, and I'm going to just draw a geometry which is a little bit more complex than the one that you can construct using the built-in wizard. So here we have the geometry. I can now turn off the grid. What I need to do now, once I've got a geometry, is think about support conditions. So what I'm going to do is select the geometry, and I'm going to actually filter down so I've only got the boundaries, so the exterior boundaries, and I'm going to choose now the support that I want. Let's suppose simple support. Next thing to do is to apply a slab definition, and there are various ones built in. So I'm going to choose the most simple one to start with, but I could create a new one, in which case I can specify all the various details of the slab that I'm interested in. But what I'm going to do first of all is just apply a unit MP weightless definition, just for the sake of simplicity. And the last thing I'm going to do is I'm going to choose a pressure and click on the icon here, the pink one, which is shown there, and I'm going to select the entire geometry, and I'm going to assign, in this case, again for sake of simplicity, a unit pressure, but I could create a new one and specify obviously the relevant magnitude. Okay, so now I have a very simple example, and I can click solve, and I can get the yield line pattern, which you can see is not one that would have been particularly easy to have determined by hand. And I also get a solution, and the solution in this case is 7.2, so that means that I can multiply my unit pressure load by 7.2 before I get to collapse. And I can also see what that mode of response looks like using the slider bar there. And I can simply as well ring the changes. Let's suppose there's some uncertainty about whether there really are simple supports in there. Would it be conservative to assume that there aren't? How does that change the situation? And very quickly you can get the result. It has changed things slightly. It's gone from 7.2 to 6.97, and you can see that it transforms yield line analysis because there's no need anymore to do long-winded hand calculations. And I've changed the supports again, and I end up end up with a relatively simple mechanism. And you can see there the mode of response. So it's a very, very flexible tool compared with hand-based yield line analysis. So how have we been able to achieve this? Well, we've automated the yield line method using something called discontinuity layout optimization. The work was published a couple of years ago in Proceedings of the Royal Society, and the key thing is we're able to boil the problem down to a simple linear optimization problem, which is easy to solve. So how does it work? If you have a slab, here's a square slab with fixed supports as an example. First thing we do is we populate that slab domain with nodes. We then interconnect those nodes with potential yield lines, and then we use optimization to find the minimum energy solution, or the critical yield line pattern, as you can see on the right hand image. So we're looking at through all those potential yield lines, we're finding which ones are active in the critical yield line pattern. In terms of mathematics, I won't dwell on this, but basically we're minimizing energy, actually internal energy, which is the product of length times moment capacity times rotations along yield lines, subject to compatibility constraints actually at nodes, subject to a unit displacement constraint using the principle of virtual work. And as I said, this is a simple linear optimization problem, which is why we can get solutions so quickly, and it's why also we can be sure that for the particular nodal discretization that we actually have the correct, rigorous solution. One of the key things is nodal compatibility. So I've got a simple scenario in the slide shown now. If we zoom in on the node at the corner, what we're basically doing is we're summing up the rotations around the perimeter of that node such that the rotations when resolved in the x direction sum up to 0, and similarly in the y direction they sum up to 0. This is actually taken from an article that appeared in the October 2015 issue of the Structural Engineer, and what it does is it shows the analogy between nodal compatibility in a yield line slab analysis problem and equilibrium in a truss analysis problem. So it gives a simpler exposition of the method than in the paper I mentioned earlier. Okay, so just have a look at a few examples. Simplest example that people think about when they're doing the yield line method is a square slab. Basically, we're able to get very, very close estimates of exact solutions. And in fact, in the paper from 2014, we get to within 0.01% of the analytical solution for a fixed square slab with pressure load. And we're able to automatically identify fan type patterns and also corner fan regions, as you can see shown in the slide. We're also able to deal with slabs with more complex geometries and with variety of different support conditions. So the example shown on the slide now is quite commonly analysed in the literature, and we're able to get a solution which was better than could be obtained using any other technique to date. And you can see it's a mixture of sort of simple yield line patterns and much more complex regions in certain areas. Okay, moving on to a more realistic example, an apartment block floor slab. This one's actually in St John's Wood in London, and as you can probably see from the facade, it's actually got quite a complex geometry. And if we look at a plan view, you'll see also it was an example which was considered by Kennedy and Goodchild in their 2004 Concrete Centre Guide to Yield Line Design. And what they had to do by hand was consider many potential mechanisms. So you can see on the right hand slide there's various different patterns that they were considering, and they were trying to fit relatively conventional looking patterns to this complex geometry. And in addition to the complex exterior geometry, there are also blade columns scattered around in fairly arbitrary seeming places. The mechanism on the right is a sort of a folding plate mechanism, and actually that's the mechanism that we found to be critical when we analysed this slab using LimitState slab recently. And actually we found that the the floating plate mechanism that Kennedy and Goodchild was relatively accurate. It was within about 10%, but it must have taken A, an awful lot of time to find that mechanism, and B, there must have been some concerns as to whether really they had found the critical mechanism. Right then, I'll move on to just a few words about LimitState SLAB 2. Actually, I think I'm going to probably hand over to briefly back to Tom Pritchard from LimitState. He's just going to say a few words about some of the new features in version 2. So, hand you back to Tom.
Thanks, Matthew. So in LimitState SLAB version 2, we have added quite a few new features to it. The most exciting of which, I guess, are the various new support types, which I'll demonstrate shortly, which include partial fixed T, knife edge, and liftoff. As well as that, we've also added a new rigid structural definition to the materials library, and also improved the CAD import functionality so that you can bring in your problems from CAD in a better way. So I think the easiest thing for me to do is actually just to demonstrate to you the different types of support that we've added to it. So the first off, if we look at the knife edge support, and that was actually something that came to us as a request from a customer, and we added it into the software. So if you do ever have ideas about things that may improve the software, then do feel free to send us an email, and we'll be happy to take that into consideration. So what I'm going to do is just start with a new project, and we'll have a standard rectangular slab. Sort of go over the project details, but if we make it just standard, sort of 1 meter by 1 meter square, and if we start off with simple supports all around the outside, so have the sort of standard unit MP weightless structural definition and unit pressure, and we'll start with a medium nodal density. So it should be relatively quick to solve and finish. And you can see here that we've ended up with a square slab with the simple supports around the outside. If I just click the solve button, it should be pretty quick actually what I'll do here. So we've got an adequacy factor on the applied loads of 24. I'll then just make some modifications to that. So what I'm going to do is make it a 5 by 4 meter slab. We'll change the top and bottom supports to be free, and the left and right we'll make fixed. So if I solve that now, we can see we've got a very simple failure mechanism through the middle, which is just a straight line and an adequacy factor of 0.64. So what we might want to do is consider having a knife edge support in the middle of that slab, which will then fix the slab against translation, but assume that the slab overlying it is continuous, with moments and rotation being allowed over the top of it until such a point that the sort of hogging moment capacity of that concrete is reached, and then it will yield. So what I'm going to do is just add a boundary line along the middle, select that line, and then you can see here in the property editor just change the support type from free to knife edge. I'll just get rid of the grid, and you can see that the hatching along it there sort of shows you that it's now a knife edge support rather than just a standard internal boundary. So now if I click solve, remember previously the solution, the adequacy factor was 0.64, and we had a sort of single yield line in the middle. Now we've got 2 yield lines, one each side of this support and one over the top of it. And if I just animate it, you can see here, so that was quite quick, so I'll bring it back. We've got these two sort of book type failure mechanisms to either side of that knife edge support in the center there. So if I just unlock it, one of the things we might want to do is potentially take away that support on the right hand side, see what effect that has. So if I now solve that again and animate, what you'll see is basically a failure of the slab over that knife edge with an adequacy factor of 0.32, so it's reduced down again quite quickly. And one of the good things about LimitState slab is you can conduct sort of what-if analysis. So I mean, what if this knife edge was actually further to the right? So if I select it and then make the position at 3.75 meters away and then solve again, you see what happens. So now we've got the yield line is actually moved into this larger section of the slab, and you can see that you've got sort of rotation of the slab around that knife edge support with the failure mechanism on the left there. So that's a very quick sort of introduction to the knife edge support. One of the other things that we have introduced into the software is actually liftoff. So if I start a new slab and we'll make that again 1 meter by 1 meter, simple supports around the outside. So remember this from just now, our solution should be 24, which it is. If I then select these external boundaries, we can see here in the property editor that support liftoff is currently set to false. If we set that to true, what that means is that translation downwards is restrained, but the slab can lift off those supports, so move upwards. So with that set to true, we can solve it again. You can see now we're starting to get a fan type mechanism starting to appear around the edges, but if I then animate that, you can see that at the corners there it's actually lifting off the supports and moving upwards, and similarly the adequacy factor has reduced down from 24 down to a value of about 22.2, so maybe a 10% reduction just because of allowing that lift off to occur. Similarly, something else you might want to do is allow partial fixity to the supports around the outside. So what I'm going to do here is just select them again, change our support type to partially fixed, and you can see here underneath the support type, if we select that partially fixed, we've got a support strength ratio, and that's basically a multiplier on the strength of the adjacent slab that will allow a fixed boundary until such a point as the strength of that slab multiplied by that ratio is reached. So if I solve again, we can see it's got a sort of proper fan mechanism here, and the adequacy factor on the applied load is about 34.8. If I very quickly then just compare that to what it would be if it was fully fixed, excuse me, then we can see that again with a fully fixed boundary, our solution or our adequacy factor is about 43.2, so moving up again by maybe 30%, something like that. So that's a very sort of quick introduction to the different types of boundary conditions that we've added into the software. One of the other things that we've done is added a rigid weightless material to the structural definitions. You can see here that you can select it from the structural definition explorer, and what I can do very quickly is for this problem here, if I make a section in the middle and apply that to it, it's asking me that it's already got a structural definition specified for that particular zone. Do we want to replace it? And yes, I do. So now we've got a rigid material in there, and solving again we can see that our failure mechanism has changed quite drastically, and also the adequacy factor has increased from, I think, what was 43 up to 55. And if I animate that, maybe with the grid turned off, you can see that now that section of the slab is acting as one rigid body, and failure is only allowed in the sections around that. So that's a very brief introduction to the rigid materials, and as we said, we've also improved the DXF input functionality to allow more problems to be imported. I'm not going to go into that today, but those of you who've used it will be familiar with with that function. So I think we're getting to the point now where we can have a look and see if there are any questions. Actually, what I'll do prior to that, I'll pass you back over to Matthew to round up and talk about some of the conclusions from the presentation, then we'll get on to the questions.
Thanks, Tom. Yes, so just to wrap up the webinar before the questions. So the yield line method is a powerful means of analysing the ultimate limit state, and the key thing in terms of benefits is its ability to reveal hidden strength. Big problem has been historically there hasn't been a general computer-based implementation which has limited its popularity, and people haven't really had access to it for some time. So we've solved that, and method is now available in the form of LimitState SLAB to you all as practitioners. Okay, so as Tom mentioned, now possible to pick up some questions. So if we just having a look now at what those are. Problem with audio. Not sure what the issue is there. So will there be a version with audio? Yes, there certainly will. I'm not sure what the issue was. I'm sorry if people had had problems. Okay, look at other questions. Okay. Okay. If you have a question, if you just type it into the chat window. Got a question about columns. How do we deal with columns? Well, probably the easiest thing to do is to get the software back up again. So well, actually, this various different ways of doing it. I mean, if I just make this a little bit smaller. Actually, probably better to start a new one. So start a new one. Rectangular slab, and let's suppose it's unlikely, but let's suppose there's a column right in the middle of it. What I can do is use this drawing functionality, and there's various different ways of doing it. One way of doing it is to, depending on whether it's a through column or it's a column where the slab is sat on it. But let's suppose this is a through column. What I can do is I can just put a hole in the slab, and then I can put supports around the perimeter. And if I solve the problem now, then the effects of that, the presence of that column, will be evident. And you can see you typically get a characteristic fan mechanism around the column, and a much more complex pattern. Does the program take into account the influence of reinforcement? Well, that's the software assumes that you have a plastic moment of resistance for your cross section available. So if I go to the create new structural definition. So what it's requiring you to do is to specify the hogging and sagging moments of resistance in two different directions. Now, most commonly, I guess, those directions are at 0 to 90 degrees, but you can, if you have a skew reinforcement, you can specify arbitrary angles there. So in other words, you can specify reinforcement in two directions, but you do need to calculate, as you would with a hand yield line analysis, what the section properties will be. Okay, I think if there's no more questions, I think I'll hand back to Tom, who's just going to wrap up the webinar.
Thanks, Matthew, and thanks everybody for attending today. Again, apologies if you did experience any audio troubles. There should be a recording of the webinar available later today or tomorrow. We'll send out an email with a link to that for you. So we do hope that you found the webinar informative, and as mentioned at the start, if the presentation has raised any questions that we haven't answered for you at the end here, please do get in touch via info@LimitState.com or even telephone us during UK office hours, and we'll be more than happy to speak to you about that. LimitState Slab is available to download or purchase now from our website, which is www.limitstate.com/slab. And for those of you that aren't current users of the software, then we'll be in touch over the next few days just to get some feedback, find out if you have any further questions, and maybe whether you think LimitState Slab might be useful to you. If you'd like to watch the webinar again, like I say, we should be sending out an email link to a recording of that in the next day or so. Also, please do look out for our other webinars which deal with LimitState Slab and our other software products, which we'll be sending out event notifications for via email in advance of them, and they'll also be posted on our website at www.limitstate.com/webinars. So that's it for today. Finally, I'd just like to say thank you all again for listening. Apologies for any audio troubles that you did have, and we hope to see you again soon. Thank you.